Hi, my name is John Morris, and I'm a doctoral candidate here at Clemson University in the Department of Mechanical Engineering. I'm hoping today to talk a little bit about our new research on constraint hypergraphs, which are a new mathematical framework that help us to solve the problems of interoperability with digital twins. Constraint hypergraphs can be used to represent new systems, including systems that have different behaviors and different things going on inside of them. They are useful ways to know the information about a system, be able to use it as we would want to use a digital twin. I'll go through these next couple of slides and talk about what constraint hypergraphs are and give us some examples of how we're using them currently. So first off, our problem statement is that we want digital twins that are useful and usable. And a lot of people talk about this as like an off-the-shelf or plug-and-play type of functionality. We want a digital twin that can be used by lots of different people in lots of different ways. For instance, we want a digital twin that could be bought by lots of different organizations and used by them without fear of losing its authenticity or meaning. For instance, I want a digital twin that might work in company A or company B, and wherever it's deployed, it should still maintain itself meaning as a digital twin. We also want digital twins that work together in the same context with other digital twins. Say I have a digital twin of a generator and I have a digital twin of a battery. I want to be able to plug those digital twins together and get a digital twin of how they're connected, like the whole total aggregate system. When I bring them together, I should get the behavior of the whole from the behavior of the individual objects. To talk about this, we're really talking about interoperability. I'm going to give two different approaches here so you know what I mean when I reference interoperability in this presentation. First side of interoperability is the syntactic definition of interoperability, which is where we want the definition of the things in our system representations to be maintained or authentic across all different kind of interactions. So if I have a model that references a battery, I want that battery to be the same battery that references every single other model that interacts with that first one. And this goes into the idea of what it means to be something. What does it mean to be a battery? Is it a type of battery? Are there standards or ports that I have to follow? Are there different power flows or information that I'm considering? And the idea of understanding what something is usually handled by people who work on ontologies. We have an ontological definition or maybe a knowledge web that talks about all the different information that's associated with something and make sure that that definition is consistent across all models that might reference that thing. I'm not really handling the ontological side of digital twins today. That is a big problem. It's actually one of the biggest problems we have to face is that data interchange, the data interoperability. But there are people who are working on that, and those people are not me. In this research, we're going to focus on the other side of interoperability, which is the semantics. This is really the idea that the behavior of a system should be authentic in and between every single interaction that system representation might be used in. This is the idea that if I have my battery and I have my generators and I bring them together, I should know the behavior of the same. My first model showed me the behavior of the battery. Another model shows me the behavior of the generator. Combined, they have some kind of new behavior, and the aggregate of those two models should give me that new emergent behavior that comes out of their interactions. This is what it means for models to or digital twins to be interoperably on the semantic side of things. Our hypergraph framework, constraint hypergraphs, goes a long ways to giving us the semantic side of interoperability. And it does that for every kind of system representation. That means it works for every single digital twin, which is just a representation of some real system. In order to motivate that kind of broad claim, I kind of want to give a bare bones example of a digital twin and talks about how that digital twin could be represented in a constraint hypergraph. And note that I'm not kind of drawing lines between different kinds of digital twins. In a lot of literature, we talk about digital shadows and digital prototypes and virtual twins, and all these are great. But I'm not considering hairs or splitting hairs on this. What I'm really doing is saying all digital twins, all system representations can be semantically given by our constraint hypergraph. And again, let me give us this bare bones example to really dive into what this means. So our bare bones example is the two systems that you see before you. The one on the left is a set of light bulbs. The light bulbs are wired to each other so that when one is on, the other one is off. If I flip the switch to the left, that light bulb turns off, the one on the right turns on, and vice versa if I go the other way. On the right, I have another system. It is a digital counter with two different displays that can show either 0 or 1 independently configured. This is our digital system, though it is not a computerized system. And note the difference. It's digital because it has digits, especially Boolean digits in this case, but it's not a computer. But we can still form it into a digital twin, and we're going to show how this can be a digital twin. In order to do so, we have to recognize that digital twins are meant to show information from another system. The light bulbs are my system of interest. I want to know things about it. And the digital twin should tell me those things. In order to make it a digital twin, I have to identify what things I want to know. There's lots of things I could want to know about these light bulbs, their luminosity, their dimensions, but maybe what I'm going to do to keep this simple is assign each one of them two different states. I want to know whether light bulbs are on or off. You can think about this as giving two different variables to this system. One is, sorry if I can get my slides to coincide. One is I have the first variable over here, which assigns each state to a light bulb as high or low, on or off, or in this case, I'm going to call it true or false. And then I have another variable for the other light bulb that has the same kind of states. I can apply these variables in the same way to the digital counter. The digital counter has two different displays, each one of those which can have two different states, 0 or 1. Again, that corresponds to our true and false. What we're making here is the twin part of our digital twin. The digital twin is a digital twin because it shares the same kind of states and values. If I see a 0 in the digital twin, it should correspond to being off for the light bulb, and vice versa for a 1 and being on. If I go back to my digital twin, what I can use this is I can use it to provide observations on the system of interest. So for instance, if I cannot see the light bulbs, if they're obscured for some reason, I can still measure the digital twin, and those observations of the digital twin inform me of the state of the system of interest. This is the full functionality of a digital twin, to provide observations of some system of interest that I may not be able to see. Of course, in order to provide this kind of functionality, I have to do what's called synchronization. So I have to have the states of the light bulbs synchronized with the state of the digital twin. If this 1 and 0 flips randomly, then it doesn't give me any good. It has to flip only if the light bulb turns on and off. So I have to have some kind of sensors, maybe a human, some kind of interface that allows me to observe the state of the light bulbs over here and transmute that to the digital twin. So when this thing is 0, we know that means the light bulb is off on that side. So the problem comes then, what happens if I cannot provide full synchronization? How can I then do our observations? This is a big problem because this is more often the case. It's very rare that you can get sensors for every single part of a system that you want to observe, every single dimension and every single place where it is and every single part of its velocity and dynamicity, luminosity. That's a lot of sensors, a lot of wires, a lot of bandwidth, and usually almost always we don't have the ability to do full synchronization. So what do we do in the case? Is our digital twin useless? The answer, of course, is no. And the reason it's not is because we can create models. So let's talk about what these models are. We know that we have this state. We have our system. We have the variables that we've assigned to the system that have our different states. And we have this whole set of all the states we can have in our system. This is all the information we want to know. A model can be described as representing the behavior of the system. We know the behavior of our system. The light bulbs are behaving so that one is always on and one is always off. That's how the system behaves. We can represent that by this set of constraints over here. See these arrows that indicate that if the light bulb is off, or light bulb is on, sorry, then this one is off, and vice versa. If this light bulb is off, the other one is on. These different constraints are the mathematical way of explaining behavior, and this goes back to the works of people like Jan Williams, systems engineers who have really gone through and identified the mathematical way of describing system behavior as constraints between system states. We can take these behaviors and apply them to our digital twin. We can say that if you have a 0, the other side of the digital twin, the other display should be a 1, and vice versa. 1 should go to 0. If the digital twin shares both the system states and the behavior, then suddenly I don't need full synchronization. The constraints reduce the amount of degrees of freedom in my system. And if I can't observe one of these light bulbs, I can still artificially observe the state of it by using the digital twin and the model behavioral constraints that the model gives me. So in this case, if I can't observe the light, I can know that one of the lights is off, and that links over here and tells me that the other light is on. In other words, the digital twin will show me a 1, and by observing that 1, even though the digital twin is not fully synchronized with light bulbs, I know that the other light bulb on the right is on. So this is my bare bones example. A digital twin is something that shares states, and in most cases, if there's not full synchronization, the behavior of the system of interest. So how does this work in the real world? Well, let's go back to our microgrid example. So a microgrid is an energy power grid where you have lots of objects that are sharing behavior that usually isn't connected to a greater utility grid. They're a little bit more localized. I'm going to do this example of the microgrid and use it to demonstrate what a constraint hypergraph is. Again, that constraint hypergraph is that framework for showing the behavior and the states. But I'm going to keep it really simple at first so we can see the different interactions of the constraint hypergraph and how it's used. So I'll start off really simple here by identifying 4 pieces of information from the microgrid that we might be interested as an agent in knowing. The first off is how much power are the generators producing? This is the power out of the generators. We also have this dock. This microgrid is actually being used with the Naval Postgraduate School. So this is a Navy microgrid, and they might have a dock with a number of ships there. So I've got 3 different pieces of information I want to know about this dock. First off is how many ships are ported there. The second one is what is the demand of the dock? What's its load that it's asking for? For instance, if I've got 2 ships, I might have more power needed to go to the dock so that I can keep those ships fully charged. And then I also want to know the status, which is how much power is being delivered to the dock at any given time, how much power is actually receiving based on what it wanted. These are my 4 pieces of information. I can take them and represent them in a constraint hypergraph. In that constraint hypergraph, the nodes become my system facts. These are the variables about the system. And recall that these variables are sets. They have a set of values that they can range over, and those become my nodes in my graph. The edges in the graph are the constraints between them. These constraints are represented as functions, and we're going to figure out why in the next slide. But you can see these functions are pretty simple. Again, this is a very simple example, but these are just rules for mapping between the values of one to the values of another. This says that if there are 2 ships, for instance, in my hypergraph, then there should be 7 kilowatts, 3,500 times 2, 7 kilowatts of power on the load for the dock. So the dock would need 7 kilowatts of power in order to operate. I can also have multiple arity functions. These are things that map multiple nodes together into a single one. So if I wanted to know what the current status of the dock is, I'm going to take the minimum of how much power the generators are producing and the needs and demands of the system to know what the current status, how much power is producing. So if the dock wants 7 kilowatts, but the generators are only producing 2 kilowatts, the dock is only going to get 2 kilowatts, and it's going to be its status. Because functions can have multiple dimensions, because they're multiple arity, we call it, these edges are not just simple graph edges, they're actually hyper edges, and that's why we call this a hypergraph. It maps multiple values of a set onto another one over here. You also notice these edges are directed. They go from one set to another, one node to another node, and that gives us our constraint hypergraph kind of paradigm. Let's talk a little bit about what it means, why these are functions, because this is important. This goes back to our definition of behavior in the first place. Functions are things that map every value of one set to a value of another one, to a unique value of another set. So in this case, we have a function that maps every single value of the number of ships to the value of load. If I've got 0 ships, I know the load is 0 kilowatts. If I got 1 ship, it's 3.5 kilowatts. If I got 2 ships, it's 7 kilowatts. This set that load can range over might be all real numbers. Maybe it's a huge set, but I know that for every ship that I could possibly have, 0, 1, or 2, there is a value in load that will be constrained to exist if that value in number of ships is given. So this function features a fully dimensioned constraint. And the idea with the hypergraph is that the graph is always fully constrained. There is no way to over-constrain it or under-constrain it the way there might be with linear systems or other mathematical representations. With this, because we're limited to those functions at our edges, the functions give us a fully constrained configuration of our system. If you give me a value for one of these nodes, and that value constrains other nodes in the graph, then the total combination of all those nodes is a valid configuration of my system. I'm never going to get to a place where I have some invalid number or where the combinations don't match up. The constraints will give me a valid way that my microgrid can exist based on its behavioral model. There's some interesting properties that come out of hypergraphs that I kind of want to go over now. So I'm going to have a couple of slides, about 10 or 12, that are going to go over different properties of the hypergraphs, talk about how they're used and how they can actually represent digital twins. The first, and maybe the most interesting, is that they engender simulation. This is very important for a digital twin because, again, most of the time we cannot measure all the states in our system of interest. I want to know what that light bulb is, but I can't see that light bulb. Maybe the light bulb is far away from me in a different room. Maybe those light bulbs don't even exist yet, or this microgrid is about a system that is yet to be developed. In that case, I'm simulating something in the future, and I cannot just go out and measure it with a pair of calipers. Instead, what I have to do is simulate it. And so any good digital twin has to be able to provide lots of different kinds of ways of simulation. Constraint hypergraphs do admirably with this. This is maybe one of their most defining features. If we're doing a simulation in a constraint hypergraph, all you have to do is form a path through the hypergraph. So for instance, here's a path through the hypergraph where I take a couple of inputs here and I'm going to map them to an output over here. You'll notice that because I can compose functions together, I can form a greater path that allows me to take these inputs and map them to this output over here. So for instance, if I want to know the status of my dock, maybe I can't observe how much power it's currently receiving, I can go through and simulate it by chaining together things that I do know. For instance, if I know the power out of the generators or how many ships are stored at the dock, I can go over and say the number of ships constrains the load or the demand of that dock to be 7 kilowatts. And I know the power out, and those combined together constrain the status of the dock to be receiving 7 kilowatts. So because I have these combinations of values, because I'm able to take these edges and wire them together, I'm able to end up with these simulations. The reason why these always work is because functions always compose. And if I go back to this previous slide before, you can see this. Any value that starts off over here is guaranteed to be able to make it to the value over here because the functions always compose between them. The idea here mathematically is that any function whose domain is the codomain of another function is going to be able to create a larger function that maps domain of one to the codomain of the other. So again, over here, if I have two functions represented by these gray arrows, because they compose, they have the same codomain and domain in the middle, any value here in number of ships is going to be mapped immediately to the status over here. And we can see that with our path through the hypergraph. I don't need to know load in order to know status because I can compose the functions here and here to get my greater simulation of that node on the end. Let's look a little bit more into the simulation because this is interesting and bears some fruit in understanding what this means in terms of a hypergraph and our system representation. So first off is that every simulation is formed of chained functional processes. This actually looks like a tree in the graph. Normally with graphs, our paths are chains, right? A goes to B, B goes to C, C goes to D, etc. But in a hypergraph, because we have multiple dimensional functions, we actually end up with trees. With these trees, all the leaves of our hypergraph are the inputs. These are things that we know. I know the power out and I know the number of ships. The root of our tree is the output. That's the thing that I want to know. And the functions combined together, bringing information, passing information from the known values up and up and up through the graph until you arrive at the status with the quality constraints that give you the artificial observation of that desired node. And even furthermore than just, this isn't just the only thing I can simulate. All the sets of paths in the graph show me all the possible nodes that I can simulate, all the possible artificial observations I can make on my system as provided by my models. For instance, in our hypergraph, there's actually 3 different trees, and these represent the different pairings of inputs and outputs that I can make. For instance, if I know the power out and number of ships, I can simulate the status. If I know the number of ships, I can simulate the load. And if I know the power out and the load, I can simulate the status. All these different trees give me all the different possible simulations in one cohesive model. I can break those out. Because I can do the simulation, what a digital twin, or sorry, what a constraint hypergraph does is it allows me to expose system information to an external agent. Again, this is the main way that we work with a digital twin. A digital twin's purpose is to provide information to some external agent. That might be a machine, it might be a database, it might be a computer or a dashboard, it might be a human who wants to know something. But either way, we go to the digital twin to give us information about whatever system the digital twin represents. If we know and can measure the observed information, then the constraint hypergraph acts sort of like a database. For instance, if I observe the number of ships to be 2, I can plug that value into this node. It's a historical piece of information now. And then some external agent can come along and say, I want to know how many ships are at the dock. And the constraint hypergraph will say, well, the value of this node is set to be 2, pushes out that external information, and the person receives it. Again, it's kind of like a database query. But if I don't have historical information, I don't have a measured value, the hypergraph can also perform any simulation it needs in order to get that value out. So if I come as an agent and say, I want to know what the dock is, the hypergraph can take the inputs that I do know and find a simulation that maps them to the output that I want to know and return that information. This combination of both measured and experimentally derived or simulated values gives me full access to all the information I could possibly know about my system, a full functionality of a digital twin. And that's why we talk about a constraint hypergraph as being a framework for digital twins, an underlying mathematical representation that allows us to use a digital twin fully without losing any kind of functionality. There are some more properties that I kind of want to talk about. And first off is that constraint hypergraphs are immediately modifiable. This goes a long way to making them more maintainable, which is a big problem for digital twins. Usually you get a digital twin and some person upstream has made it. They're very smart. They know a lot about the system. They made lots of models. They take all these models and they pass them off to you. You get this digital twin and you don't know about the system it represents, but you're trying to work with it and you're trying to understand it. And then suddenly something in that system that it represents changes. Maybe we bring a new battery onto the grid. Maybe the weather is different one day. Maybe we need to update the model for the generator. behavior. But as we change that model, because we don't understand what's going on, when we make those changes, the digital twins usually tend to break. They're very complex, that usually leads to volatility and become what we call brittle. Any change in the system they represent usually causes the whole digital twin to become invalid. We can't use it anymore. That is actually not the case with the constraint hypergraphs, and this is one of their biggest selling points for digital twins. They are functional representations, which means that you can change the behavior without any side effects later in the model. Let me give a contrast comparison before we go into how this works. If I take a model in something like MATLAB is an imperative solver. I can form an imperative solution by putting my inputs at the top of my MATLAB script and then having MATLAB go through and go do all the transformations to get up to some kind of outputs at the bottom of my program. And that works really well. Now, what if you as a modeler go in and change one of those functional transformations? You change a function to mean something else, or you change a variable name, or some other kind of modification. In MATLAB or any other imperative solver, which most of our simulation engines are imperative, what happens is you don't know what the effects of making that change will be. Are there other functions that use that variable name? Are there different results that are going to be changed if you get rid of one of the functionalities? If you remove a line in your MATLAB code, is the whole thing going to fail? Will it be fixable again? What behavior effects will it have? This is even more true with digital twins, where we might have people downstream that are using them that we don't know how they're going to be using our digital twin. And if we change something upstream, are the people downstream going to have their entire system kind of fall apart just because we made one change up above? With the constraint hypergraph, we have no side effects, which means that if I take an edge and I take it out or put an edge in, the only change that happened was on that edge. No other part of my system is invalidated. The entire thing remains consistent. If I take out this edge here for each number, ships, and load, these other edges, these other behaviors, totally unaffected. Nothing happens to them. They're totally consistent. They can be used in simulations as needed. If I add an edge in, again, the whole system stays working. Nothing changes. I get all my information back out. There are no side effects from changing behaviors. We get similar, though not quite the same, when changing nodes. If I wanted to add or remove a node from my system, then I do get some side effects, but those side effects are localized. I know exactly where they happen and how they can affect them. If I bring a new node in, I take a node out, or I change what values that node can be. This is like changing a variable. Maybe I change the units on the variable, or I change which values, like I say that actually we cannot hold two ships anymore. We can only hold one ship at our dock. I change in the values it can range across. If I do so, the only thing I need to change are all the edges that touch that node, all the edges leading to it and leading from it. If I can update those edges and show the new behavior, then suddenly everything works out fine. The entire rest of the graph completely fine, no side effects, nothing's going to break. So again, it's not no side effects, but they're very localized and easy to target. This makes them much more maintainable. As a user of my digital twin, I don't need to know the behavior of the whole system. I don't need to know how everything else works. I don't need to know all the intricacies of all the different parts. I only need to know the part that I'm maintaining right now. If I want to add a new battery, I only need to know how that new battery works. Plug it in, the edges will fully wrap into it, the nodes will fully update, and everything else remains consistent. Very, very modifiable and maintainable because of that. Another property is that we can do model comparisons. So a lot of times we want to know information, but the models will tell us. But in order to do that, we need to know information about the model themselves. You can think about each one of these edges as a submodel. Together, they create a big model, and then taken apart, there are their own models too. Every subgraph is a graph in and of its own right, and every edge is a model or a submodel in and of its own right. So by applying edge weights to these edges, we can actually get characteristics of the models themselves. This is like thinking of putting metrics on our models. One of these things, these metrics might be is computation time. Let's say I want my digital twin to run in real time, or I need it to finish computing before, the end of the day or whatever it might be. I can say each one of these edges have a certain runtime, and I assign it a number. And then the path, the simulation that I'm composing through the graph, will be able to tell me the total runtime of that simulation. If I have multiple paths that I can run, for instance, here's multiple ways to solve for status, then I can actually look at those paths and compare them and say, this one, even though it's got two edges, is shorter edgewise or weights-wise than this one over here. So maybe this one will be faster and I want to run that one. And this way I can do comparisons between models. We call this model selection. I can compare and find the best model for computation time, whether it's available, if I have the resources necessary to run these models or simulations, if I can do parallelization and break these out into different computers. We can even do some stuff with quantifying uncertainty and the fidelity of our models. When we want a higher fidelity model that's got lower uncertainty early on, and then later we want to choose a model that's got more fidelity but a little bit less uncertainty. and a little bit less uncertainty, but maybe a little bit more higher runtime. Solar edge weights allows us to do model comparison and selection. Finally, our graphs are composable with each other along their shared nodes. This is a very important point because digital twins, as we talked about before, have a lot of problems with be semantically interoperable. Again, this is the idea: if I take my generator, I take my battery, I put them together, there should be some new behaviors, and I want to know what those new emergent behaviors are. We can get those emergent behaviors by doing what's called a union operation. That's when I take my graph, my two different graphs, and I combine them along their shared nodes. For instance, in this case, I have a new model of a generator, which adds some new nodes to this graph. This is its own graph on its own, completely independent and completely consistent. The generator has a new value of being on or off. It also has a fuel level, and that allows me to solve for how much power it's producing. That's great. That's its own graph. It exists all by itself. I also have our original graph, which like that power up from the generator to the status of the dock. I can take those and combine them along this shared node right here. When I do so, what I end up with is a larger graph, and the interactions between these things are shown in the emergent, are shown by the combined paths from the function composition. When we want to give a definition for emergence, it's kind of complicated, but one adequate definition is that emergence is that I want to know how something in one system is going to affect something in another system when those two systems interact. What new interactions emerge out of their connection? And in this case, we have that. Here I know that the status of the generator, whether it's on or off, affects the status of the dock, how much power it's receiving, through the composition of these functions. If the generator is off, then the power produced by the generator will be zero. If the power produced by the generator is zero, then the minimum of these two things will also be zero, and the dock will not be receiving any power. Suddenly, I have that interaction captured in this composed graph. And all I have to do is find those nodes that they share, where the values are, and bring them together, and the new behavior emerges out of that composition. There are some technical difficulties with this, on which I'm not going to get into this presentation, but you can read some of our papers that are cited in the corners of these slides that go into what this actually means and how we're actually solving for emergence. There are some theoretical proofs that still need to be worked out for how we can prove that all the behaviors are captured. But at a gist, this is the highest level and most important part of these constraint hypergraphs. They can give us all the emergent behavior that comes from bringing systems together. This is how we solve semantic interoperability. So let's compare these to the state of the art. Right now, if I wanted to make my digital twin, my full hypergraph, what I have to do is connect all the different information from all my different models and different software together into one large simulation. So for instance, I might have information in database coming from sensors, maybe from clock synchronizers, or different models. I want to take all that information and combine it together into one single system representation. There's even more difficulties with this, in that usually in order to do that, my relationships have to be simulated using complex software. Maybe I need to run an FEA analysis and I need to call ANSYS structural or ANSYS mechanical to do some kind of structure analysis. Maybe I want to actually know how my power grid is going to behave. Homer Energy is software for doing power grid simulations, and I want to pass information to Homer, have it do its simulations, and spit out some kind of results for me. A lot of our complex simulations require complex software. And the only way we have right now to interface that is hardwired connections. I take information from one place in my system, I pass it to the software does its thing and passes me back some information. We call this a port-based connector, where I say, here's the information I'm going to be sending you, you take that information, handle it, and spit back the results that I'm looking for across that same connection. This works well if you have a very static system where everything is supposed to be connected in the same way. I know what kind of FEA analysis I want to run. I know exactly what kind of software or simulation I need to run in Homer. I know exactly what MATLAB script I need to use. Unfortunately, that is not how most of our digital twins work. Our systems that we represent are messy, they're dynamic. We need to bring things in and out of them. The models change, they update from time to time, and this complex hardwired port-based approach becomes very, very brittle. Let me give you some numbers to this so we can actually see this. If you want to think about this, you might want to think in terms of how many simulations you can form from a system representation. This is an example of one type of simulation. This is a block diagram, I think, done in Simulink. This does a pendulum model over here. So over here we have all of our inputs. These are all the things that we might know. The model tells us how to take these inputs and transform them into some kind of output that we might want to know on the other side. That's great. That gives us all we need to know for that combination of inputs and outputs. But for any system representation, we might have any number of input and output combinations. What is the total number of input-output combinations we might need to run? Well, it actually relates to the number of edges or relationships in your model. It's the combination of all the different possible relationships between variables in your system. That number is over here. It's n, the sum of n minus 1 times n choose I. This is a combinatorial number that grows very large, factorially large, right? So if you have 5 variables in your system, you have something like 80 different simulations you could compose. If you have 20 different nodes in your system, then you have like 10 million. And suddenly you have a large number of simulations. Each different combination of edges requires its own imperative model. So if you're working in block diagrams, for every single input-output pairing, you have to make a whole new imperative model. And if you have 20 nodes, that means you need to make possibly up to 10 million different simulations. The number is actually even higher than that. This is a low bar estimate because you can combine edges in different ways. You can come up with different kinds of edges too. So we might have more, but minimum 10 million different ways to get all the possible combinations of inputs to outputs. How does this differ with a constraint hypergraph? Well, constraint hypergraph is declarative rather than imperative. Declarative means that it takes all the information and puts it into a single representation of the system and then can automatically or autonomously back out the simulation that you want to run on it. So rather than having 10 million different simulations, in here we have all the simulations represented as a graph. And then I, as an agent, come in and say, I want a simulation that takes me from these inputs, bolded in black, to these outputs, bolded in blue. And then the autonomous solver can do simple pathfinding to find a path between my inputs and my outputs. In other words, it's composing a new simulation on the fly. So all my simulations are discoverable from the hypergraph as I need to, rather than manually defined in all 10 million different file formats. This really increases the flexibility and generality of our systems and makes it so that we can quickly find all the information we need that would be useful for a digital twin. You can see here, this is the same hypergraph represented twice. I can have 2 completely different simulations for 2 different outputs from the same hypergraph. And all I'm doing to find these simulations is pathfinding. It's pretty simple mathematics, actually. We're just going through and finding a composable tree from our inputs to our outputs. That simplicity really helps us when we're trying to do this complex simulation. But this goes beyond just doing algebra. We're not just talking about multiplication and subtraction anymore. We can do really complex simulation with this. In fact, we might say we can do all forms of simulation, because all simulation really turns out to be is composing functions, functional constraints, determining how the behavior of my system is going to set the value of some fact about my system that I want to know. Because of that, we can map these into really complex stuff. Things like finite element analysis, or things like computer-aided design and 3D modeling. For instance, here's an example that we did with a camshaft. We take this, or sorry, crankshaft. We take this crankshaft. We might want to know some things about it. Maybe we want to do some analysis to figure out its moment of inertia, or its density, or how it's spinning and its acceleration in different firing characteristics in an IC engine. If I take this crankshaft, I can understand things about it if I can use the solid geometry produced from some CAD engine. In this case, we've linked our models up with Onshape. Onshape, it now becomes not a software that we're passing information to and getting information from, but rather something more like a calculator. I'm using Onshape to calculate the values in my hypergraph so that I can get the values out that I need, for instance, like the moment of inertia of this crankshaft. In this case, I pass in some inputs, these are our dimensions, and I use Onshape's API to wrap its functionality, again like a calculator, into my hypergraph. So this takes my inputs and passes them. I can do different calls. I can make different extrusions. I can make different planes. You can see document IDs being passed here, different operation types, but I can rearrange this CAD model in any different way I want. I can make it longer or shorter. I can make it move it in different ways as long as I have the API calls to wrap it into my constraint hypergraph. And at the end, I can get out the density or the moment of inertia or whatever else value I need to pass into my dynamic simulation later on. What we're doing here is not hardwired connections to Onshape. Rather, we're taking Onshape's functionalities and we're exploiting it into our constraint hypergraph. So rather than passing information to an external agent and passing off and losing our data, we're collecting all of our data into one representation, our constraint hypergraph, which shows us all the different combinations simulations we can run, including the software we might need to run those specific edges in that simulation. So I can map this Onshape model with an FEA solver easily and just take that data straight across and run whatever kind of FE analysis I need using my Ansys Workbench or COMSOL or whatever my simulation software might be, connecting it over so that I can get the overall simulation explored out of it. In order to do this kind of declarative solving, what you need is what's called a agent of exploration. This is something that can go into the model, find the answers you're looking for, and bring them back out to you autonomously without you having to do it yourself. You can see this in declarative solvers like Modelica. In Modelica, you define a model, you tell its relationships, and then you say solve. You just type in the word solve, and Modelica has a proprietary solver that in the background takes your model that you defined and solves the differential equations relationships to give you out whatever you're trying to solve for. This works great for differential equations, but it's kind of hard to expand that out. It's hard to connect, say, CAD or a database into Modelica. It doesn't immediately do those interactions because it's proprietary solvers for solving differential equations. But constraint hypergraphs are for any model, any system, any simulation. And because they're so general, they can handle all that information connections. The way we've implemented this is on software called Constraint HG. It's a Python package. You can pip install it by going pip install Constraint HG. You can also see this open source on our GitHub repo. I'll post a QR code at the end of this presentation so you can see that. But what this does is it does simple breadth first searching. Again, solving these hypergraphs is as simple as doing pathfinding. All this software does is it takes in a set of inputs, takes in a set of inputs, takes in the output that you want, and does solve for it. These calls are pretty mundane. You just say, I want to know this node value, and it finds a path from what you do know to that path you want to know and gives you back the value out of it. That's a full complex simulation in one tiny little call passed to this autonomous agent. Okay, so this is the theory of hypergraphs. Now let's take this and give some actual examples beyond just our simple case. And let's explore this to the full case. What we have here is an example with a naval microgrid. This is a microgrid for the U.S. Navy, being done at least with people at the Naval Postgraduate School, researchers there. If you want to know more about this example, you can go into GitHub. We have everything publicized here. You can see the demo, all the different nodes. You can use it yourself and see the functionality of it. But I'll go through a little bit of it here and use it to help us teach what constraint hypergraphs can do for large complex systems. You can see here in the macrogrid, we have 12 different objects. We have some buildings that need power. These are our loads on the system. We also have things that can produce power, solar cells, batteries, generators. We also have the utility grid, which may or may not be connected at any given moment to our microgrid. As a modeler, I might want to know things about this microgrid. For instance, how is it going to respond to failure? What are the best way to bring the batteries into it? How should I connect this system? We might want to know how is it going to react if the weather gets cold and fails like it did in Texas a couple of years ago. I want to know the behavior of all these things collectively. How would the total aggregate system behave when I bring all these individual digital twins together into one cohesive whole? And the answer is this. It's a little messy. This is a complex system. There's a lot going on with it. There's 200 different state variables. That's 200 different ways that we can characterize change in our system. And there's over 500 edges. These are 500 different constraints that show how the system might behave. And again, because we're using functions, no matter how many edges we have in here, we're always fully constrained. Each path through this system is going to be a valid configuration of this microgrid, a valid way that this microgrid could exist, depending on the model that we've given it. As we take this, we can understand a little bit about how this hypergraph is working. First off, we do not have objects in the hypergraph. There are no nesting, there's no attributes on things, there's no parameters attached to each one of the nodes. The nodes are a single value each, or a set of values that manifest one single value at a time. So if I wanted to know what the battery is, there is no battery in the hypergraph. There's only the values associated with the battery. These are more like regions or collections of nodes. Those are the things that reference things. Things or objects are useful for me as a human to understand. I want to know what a battery is and what a utility grid is. But for the hypergraph, all it cares about is the information associated with the thing. The battery state, its level, what it's connected to, how fast it can charge and its efficiency, things like that. And so I put all that information as nodes, and those nodes stay as a flat, non-nested representation. On the pro side, what that means is that all of information is immediately accessible to all other information in the system. It's not encapsulated behind any kind of walls. If I want to know how the diesel generator affects the battery state, I can see that by tracing out a path through the hypergraph. I don't have to dig down into different levels of abstraction to find that relationship. This is a fully flat, unnested representation. But you can still see our regions here. So our green things are the information associated with the battery. The red is associated with the utility grid. The blue nodes are the ones that are associated with buildings. Here are our solar cells in yellow and our generators in purple. We have some other simulation stuff like connectivity and their time sequences. Those are all shown in the graph. And those are kind of the areas of the nodes that come together, the collections of which are what we typically would associate with objects from a human perspective. We can also include all kinds of simulation. Again, this is a big part of a constraint hypergraphs as being a useful digital twin framework. Any model, any system, any time of simulation can be represented in a constraint hypergraph. That includes our dynamic simulation, where we want to say like how things are changing in time. For instance, here's some time steps. We have different time scales in here, things moving over years and months and weeks and days and seconds. And all those time scales are handled in the dynamic simulation of our constraint hypergraph. We have database queries. We can do SQL queries, or we can do, I think there's some queries in here going between CSV files, and we're just going to the files, grabbing historical data and bringing it back out. If we're using that information, we can represent that information as a node and do those kind of queries and get those information mapped out. We can also do file input output, which is historically a difficult thing for a functional model to do. But if our file is just another piece of information, we can say, here's the information, here's where the file is stored, the file path, and let's pass in all the information we've stored as a big collection of data into that file. And we can do logging or any other kind of input output that we might need to with file systems. We can do linear equation solvers. So here's some matrices. We can solve that linear system and get the matrix out. We can form and decompose matrices. We can also do random models, stochastic modeling, where even though this is a deterministic simulation, I can pass in random variables for a value, maybe a probability or probability score, and do some kind of Monte Carlo simulation or other kind of randomized simulation trials that allow me to see different randomness inherent in the system. Okay, sorry, I'm moving forward a little bit too fast. This is our hypergraph of our microgrid, and it gives us the ability to represent the microgrid in totality. This is called universal, we're calling this universal simulation. And the idea here is that as a modeler, if I want to know anything, let's say the state of the battery at the 12th hour of its running, all I have to do is go up to my hypergraph and say, solve the path or find a simulation path for the node of the battery state at the 12th hour simulation. One call, that's all. And then the the software will autonomously go find a path from all my known inputs to that output and return to me a value. The state of the battery at the 12th hour is 14 kilowatts. Done. That's all I have to do as a modeler. And this becomes my reference bank, again, my information generator, to act as a digital twin to give me information about the system that I need to observe, either measured values or simulated. We're very excited about this. We think this solves a lot of our problems with the semantic interoperability of digital twins and can be very useful. It is not a silver bullet. There are, of course, limitations. And at the end of this presentation, I'll go through these limitations now. So you know that this is not just solving everything, but there are some things that still need to be worked on and need to be developed before this is a totally useful simulation framework. First off is the complexity problem. The idea that constraint hypergraphs can represent all systems and all models means that they can take in all information. They're not going to lose any meaning. They're not going to lose any relationships. They're not going to lose any data. That being said, if you can take in all information, then that information tends to be very large and complex. If you can handle all different models, then if you bring all models in, the resulting collected model is going to be pretty complex. And we do deal with very complex hypergraphs, which you can see here. Even for something as simple as this microgrid, 200 different ways that this can change. And this is, obviously scalable. We could get into the hundreds of thousands of different nodes here. That complexity is not really an issue of the hypergraph. If you were going to run a simulation from node 1 to node 2, the complexity of that simulation is the exact same complexity it would be if you did it in a different framework. If I make my Simulink block diagram and run that simulation, it will be the exact same simulation that is if I ran it from these nodes to that node. So the complexity for simulating, unchanged. We're not changing anything about the models or the information. We're not adding any new relationships or taking any away. So we're not adding or changing that complexity. If it took you 8 hours to run an finite element analysis before, it's still going to take you 8 hours, and we're not going to change that in any way whatsoever. What we will add is if we're trying to discover that simulation in the first place. If we don't know the simulation path, then we have to do a pathfinding search. And the larger the system gets, the harder that pathfinding becomes. There are some complexities here dealing with cycles and some kind of subnodes that make pathfinding a little bit more complex than it needs to be. We're still working on solutions to that. We are fully solvable right here, at least if you have infinite time, but sometimes it can be difficult to navigate through this graph and actually find the simulation that you're trying to run in the first place. So ongoing problem with the complexity issue in terms of you can't just represent everything immediately, because then it becomes hard to discover out the simulation that you've buried between all these different models, at least if you need it before the universe expires, right? The other thing is that these are complex in that they're visually complex. They're hard to read. They're great for computers to read. If you want to autonomously go through them as a software, easy setup. The mathematics fall out quickly, and a computer can easily solve these, quickly come up with your pathfinding solution, do the simulation. For a human to do that, Not so easy. And you already know this from looking at this. If I was going to tell you that this is a microgrid, I would be right. All the behaviors are captured here. Everything about the microgrid is on here. But you as a human looking at this, you don't know anything about it. Like you can't read in this. There is no way to find some kind of human comprehension to understand how the system is working. That is a bit of a problem, especially for modifying. If I'm a human and I don't know how the system works, then it's hard for me to figure out how to modify it. We talked about how these are immediately modifiable, and they are. There are no side effects. But that's if you can identify which edge and which node you need to modify. And that's not immediately available from just looking at these graphs. One way that we can solve this is by saying, let's not make the models in the constraint hypergraph. Let's start by making the models in the frameworks that actually make it useful to do the modeling. So for instance, if you want to make a solid geometric model, you should probably do that in CAD software. CAD is much better for working for geometry. You can see it, you can move it, you can rearrange it. So go to your favorite CAD application and make your solid geometric model. Great, that's great. After you've made the model in the framework that's conducive for that modeling process, then pull it over back into the constraint hypergraph. The idea that all models and all simulations are available with the constraint hypergraph means that any model you make in any other framework can be deconstructed and reconciled in a constraint hypergraph and maintain that consistency. So make your FE models, finite element models, make your meshes, make your solid models, build your things in MATLAB and your block diagrams. And then once you have all your relationships figured out on all those nodes, then you can bring them to the constraint hypergraph, and the constraint hypergraph will link them all together, maintain the relationships, and give you one machine readable representation of your system. And that is still fully usable as a digital twin. Okay, so we're wrapping up here. We finished up the theory and we finished up our practical example. Now I kind of want to talk about the implications of what this means for us as modelers. One of the things that we want to kind of quell right away is that we're not replacing any work that's already been done in science and modeling. We're not adding new information. We're not taking away anything with software. We're not replacing AI even, or any kind of scientific work. All that work that's been done for generating information still has to do. What we're providing is a structure for organizing and capturing that information. For instance, if you're a modeler and you have this model of A, B, and C, you have another model of D and E, and you want to figure out the relationship between the two of them, you still have to do all the work of modeling. Maybe you do a linear regression to figure out how C and B together vary against D, and you come up with some linear model. If you have a physics-based equation that allows you to see how C and B physically relate to the value in D, or maybe you ask ChatGPT to figure out the relationship and it goes through its large language model processing its neural net and comes up with the relationship between them. The idea here is that you still have to do all that work. We're not replacing it. But once you have that relationship, you can plug it in here, get that edge, and suddenly your hypergraph holds that information and allows you to return it so you can use it for future simulations. We are capturing and efficiently giving in a lossless format all the information about the meaning, the relationships, the semantics about our systems. So in conclusion, we're offering constraint hypergraphs as a new framework for representing digital twins so that digital twins can be composed, redeployed, created, and adapted without any kind of loss of meaning in any system that might be used in, any kind of context that might be employed in, or any kind of aggregate systems that might be used to create. The reason we're doing this is because our constraint hypergraphs gives us the full functionality of a digital twin, in that it allows us to both observe all the information of a system, both the information that's been measured and the information that needs to be simulated. It connects all that information into a meaningful network and allows that network to maintain consistency even across different compositions and between different input-output pairings. As we wrap that into a single model, we're able to use this as an effective digital twin for whatever we needed to use that digital twin for. If you want more information, you can find stuff on our GitHub repository for our package. Again, Constraint HG is the name of that. You can follow the QR code here to get to that package. The Constraint HG has both all of our demonstrations that we've had so far and how to use it. And it also has on this wiki an overview of constraint hypergraphs, some examples with figures and data, and also how to use the software yourself. So if you want to use this to represent your systems, you can go ahead and learn how to use this in your own work. We're also happy to collaborate. If you'd like to collaborate on this, please reach out. My email is on the screen at jhmrrs@clemson.edu. You can also contact us through the GitHub repository, find our profiles there. We would love to engage with you and show how this can work for your systems and find out how we can improve this together so we can really find out how to use or make digital twins that are both useful and usable by other people going forward into the next generation of technology. Thank you so much for watching this, and we look forward to collaborating.